Hello student, welcome to Ideal Science Katta YouTube channel, Rotational Dynamics lecture series, and this is the part 10. If you didn't see the last 9 videos, please see it. Today we are going to start new point. The point is the expression for rotational kinetic energy of rotating body. So we are going to start the expression for rotational kinetic energy. What is meant by rotational kinetic energy? The kinetic energy possessed by body due to rotational motion. If the body is rotate about itself, then it has rotational kinetic energy. And what is the translational kinetic energy? If the body is moving along straight line, suppose this is the body and this body is moving along straight line, then body has translational kinetic energy. So let's start it. Consider a rigid body rotating with a constant angular speed omega about an axis perpendicular to its plane and perpendicular to plane of body. Suppose this is the body and this is the axis passing through the any points of the body, certain points, and this axis is perpendicular to the plane of body, and body is rotating about this axis with constant angular velocity omega. Let body consist of number of particles of masses m1, m2, m3, m4 up to m of n, situated at a distances of r1, r2, r3, r4 up to r of n from the axis of rotation respectively. So this is the body, rigid body, and this rigid body consists of number of particles m1, m2, m3, m4 up to m of n. So this is the first particle of mass m1, this is the second particle of mass m2, this is the third particle of mass m of n. The first particle is at distance r1 from axis, this is the axis, and from axis of rotation the m1 particle is at a distance of r1, m2 particle is at a distance of r2, and last particle m of n is at a distance of r of n. As the body rotates, its all particle perform UCM with the same angular speed omega. Suppose this body is rotating about this axis, so these particles first, second and third, these three particles perform uniform circular motion with the same angular speed omega. जेवढी बॉडीची अँग्युलर स्पीड ओमेगा आहे तेवढी प्रत्येक पार्टिकल m1, m2 आणि m of n या तिघांची अँग्युलर स्पीड असेल ओमेगा. बट linear velocities of each particles are different. m1, m2 and m of n has the same angular speed omega, but first particle, second particle and third particle have different linear velocity. So see here, this is the first particle having linear velocity v1, so v1 equals to r1 into omega. This is the second particle, so v2 equals to r2 into omega, and up to v of n, r of n into omega. Omega is constant in all terms. See here, omega, omega and omega. We didn't use 1, 2 and n suffix for omega. v1 equals to r1 into omega because for first particle m1 r1 is used and omega is constant. For second particle r2 m2 is used and omega is constant. So see the next. Translational kinetic energy of first particle is given by, this is the first particle. So the translational kinetic energy of first particle is given by kinetic energy and suffix first means first particle 1 upon 2 m1 v1 square. This one is used for first particle. So kinetic energy of first particle equals to 1 upon 2 m1 v1 square, but v1 equals to r1 into omega. Previous slide मध्ये आपण ते बघितलेलं आहे, v1 equals to r1 into omega. So put here on in the place of v1. So kinetic energy suffix first equals to 1 upon 2 m1 r1 square omega square, because v1 square is here, so r1 square omega square. kinetic energy of first particle is equal to 1 upon 2 m1 r1 square omega square. This is equation number first. This is the rotational kinetic energy of first particle. Kinetic energy of first particle is equal to 1 upon 2 m1 r1 square omega square. This is the rotational kinetic energy of first particle. तर ही फर्स्ट पार्टिकलची रोटेशनल कायनेटिक एनर्जी आपण सॉल्व केली आहे. दिस इज इक्वेशन नंबर फर्स्ट. Similarly, rotational kinetic energy of second particle is given by. So we are going to find the rotational kinetic energy of second particle. So kinetic energy of second particle equals to 1 upon 2 m1 is replaced as m2, r1 square is replaced as r2 square, and omega square is as it is equation number 2. This is rotational kinetic energy of second particle. Similarly, kinetic energy, rotational kinetic energy of last particle, this is nth particle. So kinetic energy of nth particle equals to 1 upon 2 m of n r of n square omega square. This is equation number third, and this is the rotational kinetic energy of nth particle, last particle. So these three equations are most important, first, second and third. Kinetic energy first equals to 1 upon 2 m1 r1 square omega square, equation first. Rotational kinetic energy of first particle. Similarly, kinetic energy second equals to 1 upon 2 m2 r2 square omega square, equation number 2. And kinetic energy of nth particle 1 upon 2 m of n r of n square omega square. So these three equations are most important. Thus the rotational kinetic energy of body is given by kinetic energy of body. We are going to find the kinetic energy of body. So kinetic energy of body means kinetic energy of first particle plus kinetic energy of second particle plus up to kinetic energy of nth particle. So the addition of kinetic energy of all particles means kinetic energy of rotating body. So kinetic energy is equal to kinetic energy of first particle plus rotational kinetic energy of second particle plus up to kinetic energy of nth particle. So what is the equation of kinetic energy of first particle? Kinetic energy of first particle equals to 1 upon 2 m1 r1 square omega square. So this is the value of kinetic energy first, we put here. So 1 upon 2 m1 r1 square omega square, plus sign is as it is. Kinetic energy of second particle's equation 1 upon 2 m2 r2 square omega square, plus sign is as it is. Kinetic energy of nth particle 1 upon 2 m of n r of n square omega square. So this is the equations of kinetic energy. So adjustment, see here adjustment, this 1 upon 2, this 1 upon 2, and this will take constant here 1 upon 2 omega square and omega square will take constant here. So 1 upon 2 is constant and omega is also constant. So what will remain in bracket after taking constant? m1 r1 square m1 r1 square m2 r2 square m2 r2 square m of n r of n square m of n r of n square. So we write in brackets this term. So if we see that, then m1 r1 square m2 r2 square and m of n r of n square, this can be written in the form of summation. We can write in the form of summation. In last video we saw that m1 r1 square plus m2 r2 square plus up to m of n r of n square is replaced as summation. So kinetic energy is equal to 1 upon 2 in a bracket summation of m I r I square. I started from 1 end up to n. I's value started from 1 because we see here m1 r1. So i's value started from 1 and last value is n. So see here the last value is n. So last value is n, bracket close, into this omega square. But summation of I started from 1 end up to n mi ri square equals to I. This is the formula of I. I means moment of inertia. So this bracket will replace as I. kinetic energy rotational equals to 1 upon 2 into I omega square. So this 1 upon 2 is as it is here, and summation of I mi ri square, I started from 1 end up to n, this bracket will replace as I, so I is here, and into omega square, equation number 4. This is the rotational kinetic energy of body. Equation 4 is represent rotational kinetic energy of body. Rotational kinetic energy's equation is kinetic energy suffix ROT. ROT means rotational. Kinetic energy rotational equals to 1 upon 2 into I into omega square, where I means moment of inertia and omega means angular velocity of rotating body. Translational kinetic energy of body is given by, we know that kinetic energy translational is equal to 1 upon 2 mv square. So this is equation number 5, where m means mass and v means linear velocity. And in previous slide, in equation number 4, we obtain the equation of kinetic energy of rotational, that is 1 upon 2 I omega square. So from equation 4 and 5, it is clear that moment of inertia in rotational motion is analogous with mass in linear motion. So see here, this mass, that is m, is analogous with I, that is moment of inertia. This is the relation between moment of inertia and mass of linear motion. Moment of inertia of bodies depend on, first, distribution of mass from axis of rotation, individual masses, and position of axis of rotation. So moment of inertia is depend on these three quantity. First, distribution of mass from axis of rotation. Suppose this is the axis of rotation, and from axis of rotation, distribution of mass, either mass will be close or is at longer distance. This is called as distribution of mass. And individual masses, this is the individual masses, m1, m2, m3, m4 up to m of n, and position of axis of rotation. Suppose see in the figure, axis of rotation is passing through this point. It might be passing through any point. Axis of rotation will be at any point. So position of axis of rotation is also describe the moment of inertia of body. Thank you for watching video. If you like our video, please subscribe our YouTube channel. Thank you.